Hey everyone, today we'll be going over Leetcode problem 98, Validate Binary Search Tree. This is another problem off the Blend 75 list, which is a list of problems commonly asked during technical interviews. In this problem, we are given the root of a binary search tree, and what we want to do is determine whether or not this is a valid binary search tree. We're given three conditions to validate our binary search tree. We're told that the left subtree of a node must only contain nodes which have a value which is smaller than the node itself. The right subtree of a node must only have values which are greater than the node itself. And finally, that the right and left subtrees must also be binary search trees. Because of this last condition, we know that we are recursively applying our check to our specific node and then to its left and right subtrees. Therefore, in order to solve this problem, we will use a recursive algorithm known as recursive depth search. What we will do is start from the root node and check to make sure whether there are not any violations up until this point. Then we will go on to its left and right subtrees and make sure those are also valid binary search trees. A common mistake made by students is to forget to check an entire left and right subtree of a specific node and instead check the left child and the right child directly. For example, we have here as the root of our tree a value 5. We go and check the left child of 5, and we see that its value is 1, which is indeed smaller than 5. We check the right child of 5, and we see that its value is 7, which is in fact greater than 5. When moving on to the right subtree, we check its left child, and we see that it has a value of 3, which is smaller than 7. And when checking the right child, we see that it has a value of 8, which is greater than 7. Therefore, we might think that this is a valid binary search tree. However, if we look closely, we see that there is a value in the right subtree of 5 which is actually smaller than 5 itself. In fact, the value 3 cannot be in the right subtree of 5, because being in the right subtree of 5, this value 3 cannot exist because it is smaller than 5 itself. Therefore, in this case, we would return false. This is not a valid binary search tree. For each and every node, we must check to see whether or not it is inside a specific interval, because each and every node will have a minimum boundary under which it cannot go, and a maximum boundary over which it cannot go. Starting from the root node, we see that we have a root node of 5. In fact, this root node can have any value going from negative infinity to positive infinity. When going to the left subtree of 5, we see that we can have a value which goes down until negative infinity. However, because it is in the left subtree of 5, it cannot reach 5 itself. It must be smaller than 5. So its max boundary will be 5. When going to the right subtree of 5, we know that here we can only have values which are greater than 5, and these can still go up until positive infinity. When then going to look at the left subtree of 7, we know that this value must be smaller than 7. However, because we are still in the right subtree of 5, this value must still also be greater than 5 itself. So the interval is 5, 7. Finally, when going into the right subtree of 7, we know that this value must be at least greater than 7, and then it can go up to positive infinity. Having applied these intervals, we can now fix our binary search tree. We know that this 3 cannot exist in this subtree, and we can change it to a number which is between 5 and 7, so we can include 6. Now our binary search tree is valid, so instead, in this case, we would return true. So we're going to start off saying that our left boundary will be equal to negative infinity. Our right boundary instead will be positive infinity. And what we will do is call a depth search function, passing in the root of our tree, along with our current left boundary and our right boundary. Next, we have to define our depth search function. We know that this function will be receiving a node each time, a left boundary, and a right boundary. Initially, what we want to do is check whether or not the node exists. If the node is null, what we can do is return true because we know that a null tree is a valid binary search tree. Following this, what we need to do is make sure that our current node's value falls within our specific interval, and therefore it must be greater than our left boundary and smaller than our right boundary. So if node.value is smaller than or equal to the left boundary, or it is greater than or equal to the right boundary, then what we know is that this must return false because it does not respect the interval. Finally, we want to run the same depth for search on the left subtree and the right subtree. So what we will have is that we are returning the depth for search on the left subtree, where we pass in as the root node.left. Our left boundary will remain left, while our right boundary will now become the current node's value. And this is because we're going into the current node's left subtree, meaning that every node in the subtree must be smaller than the current node. Therefore, node.value will be the max boundary. For the right subtree instead, what we must do is pass in node.right as the root of the right subtree. The left boundary, or the minimum boundary, will now become the current node's value because we're going into the right subtree of the current node, so all of the values in the right subtree must be greater, whereas the right boundary, the max boundary, remains the same. Let's make sure this runs. And we see that it works. This is a linear time solution because we are going through each and every node only once in order to determine whether or not this is a valid binary search tree. Thank you very much for watching this video. If you enjoyed it, please like it and subscribe to my channel. I'll see you on the next one.